Uh, so far what we have seen are basically two structures, two mathematical structures that we have seen. One was group, and second was vector space. And we'll start from here to define and presentations. So what is a group? Group is basically, let's say I have a set with a binary operation, let's say star. Then group needs to follow four properties that we remember. One is associativity, second is inverse element. No, before that identity, and then inverse element, right? And what else? These three properties. Okay, yeah, closure was one, but under the binary operation structure, but we say that closure is already is inbuilt in the binary structure. And then vector space was slightly different structure, but we needed another structure called field. Okay, in our cases, we usually use real field or complex field. Okay, so V and with one binary operation that we call addition of vectors and overall field. Okay, so that was the structure, and it has several axioms in order to be V to be a vector space. So here we had a binary operation star, which is G cross G to G, and for the V it was two binary operation. One binary operation, and another was with the compatibility with the field. That was multiplication with the field with this way. Okay, these were the two operations that we actually perform, and then we define what should be the criteria for this V to be a vector space. Okay, so that's fine. Now another important thing that we saw in group was the homomorphism, which is the structure preserving maps. Okay, so let us say we have two groups G and A. A homomorphism is a function if such that f of G1 times G2 is equal to f G1 times f G2. That means we want whatever the structure that was there in G, it should be followed in H. So if we can give this kind of mapping, then we call it a homomorphism. So that is understood. And in the case of vector space, what we have linear transformation as the structure preserving map. Let us say a function L, which is a map from V1 to V2. Let us say V is a vector space over the same field L. Okay. And this is also a vector space over the same field L. Okay. So now we define a transformation or a mapping from vector space V1 to vector space V2, and it will be called a linear transformation if the following two conditions are satisfied. V1 plus V2 from V1 is equal to L of V1 plus L of V2, and second one was L of alpha times V1 is equal to alpha times L V1, where V1 is a vector and alpha is a field element or the scalar, as we say. Okay, so then it will be called a linear transformation. Okay, so now let us take a set. Okay, set of let us say A is collection of all linear transformation from vector space V to itself. Okay, such that L is invertible. So what does it mean? that we take all the invertible linear transformation from V to V itself. Understand? So take a vector space. All possible linear transformation from V to V, those are invertible. That means 1 to invertible means it's the map is a bijective map. So this is 1 to 1 and on to map. Then only we can actually invert the elements. Okay, so in other words, if it is a finite dimensional vector space and we choose a basis, then L is basically some non-singular matrix. L can be represented as we saw earlier that any linear transformation for the finite dimensional cases can be represented. Once we choose a basis, we can represent it as a matrix, M cross N matrix. If it is M dimensional, N dimensional, this is M dimensional, then A can be represented as a matrix Lij, which is M cross N dimensional matrix, and this can be. So in terms of, let's say, if we consider it to be a finite dimensional vector space, and if we choose a basis, okay, 1, 2, 3, 4, 5, 6, then all this is basically a collection of all N cross N invertible matrices. So this, let us take this set. Okay. Then since this is already, let us say, this is a mapping, right? L. So what are the elements of this set? Are basically linear transformations, some mapping. Okay. So now what we see that this A has a group structure under the composition map. Under the composition binary operation, A has a group structure. How? Let us take two elements from A. Okay. Let us say L1 and L2 are two elements from A. And we define the binary operation to be L compose L2. L2 is what? L2 is a map from V to V. L1 is what? Another map, okay, from V1 to V2. So L2, what L2 does is takes any element from V1, V2 itself. What L2 will do, it will take another element, so this is L2, L1 to same vector space. So L1 compose L2 will basically take some element from here to itself. So under this composition, so L1 compose L2 is another linear map that at least we can guarantee. We don't know yet whether this is invertible or not. If it is invertible, now so under the composition again we have to check whether this is a linear transformation or not. Whether this L1 compose L2 satisfies these two conditions or not. That we can easily check. So what does L1 compose L2 do? What is the definition of composition? So it takes any element, okay? It basically does L1, L2, V. Now let us check this condition. If we check this condition, then what we will see that L1 compose L2 is L1. This is the definition, right? L1, and by the definition, since L2 is another linear transformation, one linear transformation, so what it will do is it will give us plus L2 V1, right? L2 is a linear transformation, so it will done. L2 V1, L2 V2. What are these? This is some other vectors. It takes V1 and gives me another vector from the same vector space. So this is a vector, this is a vector. So L2 takes some argument, sum of two vectors. And by again the property of L1 tells me that this is nothing but and this is L1, L2, V2. Right? So this is fine. And this is what? This is nothing but L1 compose L2 of V1. Right? This is the definition. And this is L1 compose L2 of V2. So what did we get? L1 compose L2, which is a different map, different linear transformation, but this is linear. L1 compose L2 satisfies first condition. Again, we can check the second condition here. This is easy to check. Let us take alpha V1, then what it will do? It will first take alpha into V1. Since this, sorry. Yeah, okay. Slightly lower. L1 alpha L2 of V1. This is what? This is fine. So this is the definition of composition composition. Second is we are using the linearity property, the second linearity property of L2. Okay. Now we are using second linearity property of L1, and this is what? This is nothing but again we are using third definition of composition operator, composition of two functions. So again, the second condition for L1 compose L2 operator is satisfied. So if we take two elements from A, we first check that since they are linear operators, okay, we again get a linear operator under composition. And the second thing that we have to check is invertibility. So now that I will not check here, so it can be easily shown that if L1 is invertible, L2 is invertible, then L1 compose L2 is invertible. So that means if this is a bijection, this is a bijection, then the whole thing is another bijection. So then what we see that once we take L1, L2 from A, under the composition L1, L2 belongs to A. Right? That means composition is a binary operation from A cross A to A. Right? So that now let us check the first condition of the group, okay, associative. Is this binary operation associative? Is composition associative? Yes or no? Why? Is this binary operation associative or not? associative or not? You remember very first day we derived that any function from the same set to same set, let's say if f is a function from set x to x, okay, and if we take all the collection of the functions, okay, let us say y is a set which is, let us say y is a set such that f is a mapping from x to x, then we already showed that any two any two functions under composition is another function. That is of course a binary operation, and this is actually associative under composition. Okay, so if we take f1, f2, f3, which all are functions from x to x, then under binary operation composition they are associative. Associativity is there inbuilt in the composition itself. The very first day we actually derived it. Okay. So associativity is inbuilt in the composition. So it's not particular to linear transformation or something or homomorphism or something. It's composition is associative. Okay. Second property, do we have the identity element? Why?
Because kind of a transformation which maps the vector to itself.
Vector to itself. So whether identity is there or not. So the linear transformation which takes the same vector to itself. Okay? So it does not change at all. It's identity. And is that an element of this set? Yeah, that is an element of this set because identity operator the identity linear transformation does not transform v1, v2 at all. So this is trivially satisfied and this also is trivially satisfied. So if we replace L by identity operator, identity linear transformation, so this will give me exactly v1 plus v2. So it's already trivially satisfied. Again here also, if it is identity, then it does not change the thing at all. So it's automatically linear transformation, and whether that is invertible, of course invertible, because if v goes to v, then the same identity operator takes same v to v. So it's invertible. So identity is there. Third was inverse. Is inverse there in this? So given an element, let's say L from this set, whether L inverse we have inverse or not. So under the composition operator.
It should be there because it should be there because suppose L1 has its own inverse and L2 has its own inverse.
A1 is what?
L1.
L1.
L1 and L2 has their own inverse.
L1 has their own inverse.
L1 and L2.
L1 and L2.
Since the map is bijective.
Yeah, since the mapping is bijective, it is already said that it is invertible. So that means there is a inverse that exists. Okay? So inverse is already there because it's the defining criteria of the set. So it's already there. But yeah, you can check it explicitly because the inverse that we are talking about in the elements of A are inverses of mappings. The inverse we are talking about here is the inverse that satisfies this condition. Let's say given L1, there should exist another L prime such that this is equal to L prime composition of L should be equal to the identity operator. That's the inverse we are talking about. But here, the inverse that we are talking about is the inverse of the mapping. Whether given an element which takes x to y, whether there is another element from the set which takes y to x. So that inverse, this inverse is slightly different, but this can be followed from this. So it's basically that this we have to actually check once more. You can check it, but the definition of inverse here actually will follows. So this will be followed from this. Okay. So this is a special set, okay, which are linear transformation, and under the convolution operator we saw this is a group, and this set has a name. This is called GL. This is general linear transformation, okay, of the vector space V. Okay. So far what we learned are essentially given a vector space, okay, under over field F, okay, we have another set which we call GLV. GLV is collection of all invertible linear transformations from V to V. Okay. Then GLV has a group structure under the composition operator. So GLV is a group under the composition operator. Now let us take any let us take let G be a simple any group it can be, okay, and let us say rho from G to GL. So this is what this is, and then rho comma V is called linear representation. So what did we say? G is a group, GLV is another group. Okay. Now we can define a homomorphism. Homomorphism was what? From a group to another group such that the structure is preserved. Okay. So let us say rho is a group, rho is a homomorphism from G to GL. So what it takes elements from G and sends it to GL. And another condition it said is that the structure of this group, G group, is preserved. Then this G rho along with this V is called a linear representation. So linear representation is basically linear representation of group G is basically a homomorphism from the group to the group of general linear transformation of vector space V. And V is called representation space. So this part is clear. So let's take any group, and if we can give a map from that group to GLP, to the general linear transformation group, linear transformation group of a vector space V, then we say this is a representation. So representation is actually defined by this. This is the definition. Let us take some example of this. Can you give an example? Any example? So what we need for the representation? One vector space and the group, and we have to define this map from the group to the general linear transformation. Simplest, one of the simplest example, let us say that we earlier we showed that a field, if let us say the complex field. So we showed that a field itself is a vector space. And what will be the linear transformation? What is GL of this field, this vector space? So let us say our vector space is simply the complex numbers. Okay? And what will be the GLP for this? GLP is what? All the linear transformation.
Complex to complex linear transformation. E to the or some.
Yeah, that can be one. It is basically some another C minus C. So let us say we define the linear transformation from C, we define C to C. All the linear transformation. So GL L is inverted. So now let us say L is defined from C to C. So what will L do? L will take some element from C, let us say X, and it will deliver some element Y. And let us say this is alpha times X. If you just multiply some alpha to X, that is a linear transformation. Right? So by this is nothing but all invertible is essentially, if we exclude the 0 from C, the complex number, then that's GL. Okay. And another thing is C is a group under C star itself is a group under multiplication. Since this is a field under multiplication, so this we define it to be C star, let's say. 0 is excluded from C. So now let us take, this is very trivial, let us say rho is a map from this C C star group to GL C, right? Which is nothing but C star itself. And now let us take some element from C star and it maps to Z itself. This is a linear transformation. Sorry, this is a representation. Okay, this is not a very good example. Let us say, let's think of a better example. It's a better example. Okay, so this is a very interesting example. Okay. Example 2. Okay. Let us take group of addition of real numbers. Let us take the group G to be this. Okay. Let us take group of all the real numbers. Okay. G is R and binary operation is plus. So this is a group that we have seen already. Okay. Let us take V to be R2. That means 2 by 2. Sorry, that is all, let's say, column vectors of 1 cross. All the column vectors of 1 cross. Sorry, 2 cross 1. Okay. Now give, so what are the GLVs for this? Let's say in the matrix form. What will be the GLV? Since we have already chosen a basis, the GLV are basically all the 2 cross 2, all the 2 cross 2 invertible matrices. Let us say V is R2, that is all 2 by 2. Let us say V is R2, which is nothing but, let's say, all 2 by 1 column vectors. Okay. So in this case, GLV are basically all the 2 cross 2 invertible matrices. So now let us give a map from G to this GL. So in the particular case, when this is realized, this is in the matrix form, it is generally written as the dimension of the matrix, n cross n, if it is n cross n, then n, and the field. So in this particular case, GLV is nothing but GL 2R. This is realized in the general case. And now let us say we are giving, so in this particular case it is R. From R to GL to R. So this is 2 cross 2 matrices, and let us, what rho does, rho takes an element from R, and the form of the element, the definition of the function is this. Okay. Whether this is a representation or not. So what we have to check is whether, first we have to check that whether rho is a homomorphism or not. No, first we have to check whether but whatever map I have given is an element of GLB or not. Right? So this map, we can see what is the determinant of this map. So first, this whether this is a linear transformation or not.
There the row some G to GLV, but here by real number.
Yes, yes. So we are giving an example where in the example G is the set of real numbers under the binary operation plus. Right? So this is the general definition. Given a G, if we can give a map from G to GLP, then this is called a representation. So now we specifically we have chosen G to be the real number set under the operation plus, and V is chosen to be the two-dimensional vector space over R. Understood? Then, if we choose V to be the two-dimensional vector space over R, then what is GLP? GLP is what? GLP is a collection of all the linear transformations, invertible linear transformation. So GLP is nothing but all the 2 cross 2 invertible matrices. So in this particular case, GLP is this. In this particular example, G is R. So now, what I say is, let us say we have given a map from the real number A, real number R, to the general linear transformation of two-dimensional vector space over R. So this is GL2R. And the map definition is it takes A and sends A to this matrix, this 2 cross 2 matrix. Right. Now let us see first that whether this is the correct map that has been defined or not. For it to be a map, we have to check that for all the elements of this is a simple map definition. For all the elements, whether I am sending this to correct some of the elements of this set. So this is all the 2 cross 2 invertible matrices set. Okay? So for any A, we can actually send that element to 2 cross 2 invertible matrices. Is this invertible for any A?
Determinant also.
So this determinant is always 1. So determinant is non-zero. So this is invertible. So this is a map wise, at least this is a reliable map. This is a map. Then what we have to check, not only the map, whether this is a homomorphism or not. That means we take A star B, whether this is satisfied or not. And in this case, what binary operation we have chosen? We have chosen binary operation plus. And here, what is the binary operation?
Matrix multiplication.
It is normal matrix multiplication. So this, whether this is checked or not, that we have to. Let us check this. So rho A plus B is 1. Let us check the other side. Sorry, this is the left hand side. So this is 1, A plus B, 0, 1. And what will be the RHS? RHS is rho A times rho B. This is 1 A 0 1, 1 B 0 1. And what then what we can say that rho is a homomorphism from R to GL to R. So this is another example of representation. So for the group, so in this example, what is the group whose representation we are considering? Is the group R plus. Its representation we are considering. And what is the representation space? 2 by
Column
1
by one.
column vectors, all the 2 by 1 column vectors. This is the representation space. What is the dimension of the representation?
Dimension.
It's basically the dimension of the vector space. The dimension of a representation is the dimension of the vector space. So this is a two-dimensional representation. And we check that we can give a map. We are giving a map from this group to the two-dimensional general linear transformation. So this is another representation. So this is the two-dimensional representation. This will be called two-dimensional representation of R plus. Okay. Okay, a representation. One thing is of course clear. So that is, we can always send from any group to the identity element of the GLP. And that representation, if rho of G is sent to the identity element of GLP, so this is called trivial representation. So a trivial representation is when we send all the elements from the group. So this we can always do. This type of representation, take any vector space, send all the elements from the G to the identity element of GLP. And we saw that this will be homomorphism. One homomorphism, example of the homomorphism was you send all the elements to the identity element of the other group. So if this is done, then it's called a trivial representation. So for any group, we can give a trivial representation to the vector space. A representation will be called faithful. Okay, that will come later. Some other example. Example 3 is, let us say that, so first let us say we want to give representation, let us say all n cross n unitary matrices. Let us take G to be the group of all unitary matrices. Specifically, this is called SU. So this is called UN. Or n cross n unitary matrices. So under multiplication, this is a group that we know, because if you take U and so if it is unitary means U dagger is U. Sorry, U dagger U dagger is identity. If you take U1, U2, this will satisfy identity. Matrix multiplication is associated, and inverse for an element U is basically it's a dagger. So this is a group under matrix multiplication. So let us take this example, and let us take V to be all n cross n, sorry, n cross 1 complex column. So this is essentially, now we understand. So in this case, what will be GLB? GLB will be basically nothing but GLNC. That means all invertible n cross n matrices. Now in this particular case, what is the what representation that you can kind of think of? So we have to give a map from UN to GL in that means we want to send one element from here under this, let us say U is one element. Can you think of any representation here? One of course is trivial representation. I will say. Except from trivial representation. GLP is a subset of not GLP, GLNC. GLP is abstract and GLNC is the matrix. So GLP in general is abstract, all possible linear representation that you can think of. But once this is realized as a column vector, then it has a specific form which is matrix form. Yeah, so in this particular example, of course, we have a clear-cut matrix. Yes, what you said is essentially UN is a subset of GLNs. That's it. Because this is also n cross n matrix, this is also n cross n matrix. This is invertible. So this is a subset of GLNs. So we can send the same element to itself, since this is already a subset of GLNs, and this is called fundamental representation. This we have already heard of, fundamental representation. And there can be other examples. Let's see, think of any other examples. Okay, we can give some other complicated examples, but maybe not at this point. let's give another simple example. Example, let's say 4. Okay, we'll give some example which we usually see in our everyday higher energy physics. Let us say G is Z. We know Z2. What is this group? Zn is basically E A1 to An minus 1, and the multiplication is such that e to the power E is identity. So in this particular case, Z2 is nothing but a group of two elements, E and A, and the multiplication is E is identity, basically E times E is E, E times A is A times E is A, and A times A. So E A squared A2 is up to A minus n is Z energy. And Z2 we have seen as an abstract group. And let us take any vector space. Let us say vector space is A cross B. Complex real does not matter actually. Let us take column. And what will be the representation? In this case, we always talk about Z2 group. Let's give a Z2 group so that the symmetry is preserved or broken or whatever we want to do. So we want to give a map from Z2 to, in this particular case, GL A comma C. And let us explicitly define this has to be identity, because for the homomorphism to hold, we know that the identity element of the group should go to the identity element. Right? And I have one more element from Z, and I am sending it to the minus identity. Now let us check whether this is a representation or not. Is it a representation? That is what we do, right? We say what is Z2? We say 5 goes to minus 1. If it is 2 by 2, then also it goes to, sorry, if it is a 2 by 1 column vector, minus or minus. That's what we do. But technically, if we want to define in terms of representation and all these things, then this is basically the case. Okay, so Z2 is an abstract group where the multiplication table is explicitly specified as E times A, E times A is E, E times A is A, and all these things. And for any vectors, we can give a representation from Z2 to CLX. Another slightly interesting example example can be, let us say, G in this particular case is nothing but all the complex numbers without the identity. And so this is a group under multiplication, because we have C star is basically 0 is removed from C minus the 0, the complex number set. So this is basically a, so this is a group under multiplication, under normal multiplication. Okay. And let us say V is on 2 plus 1 here, and let us say A, B, so it's basically all the 2 by 1 column vectors, real column vectors. So this is a vector. This is of course a vector space over field R. So what will be the GLV in this case? It's nothing but all the 2 cross 2 A, B, C, E, such that A, B, belongs to R and AD minus BC not equal to 0. It's basically this another name for it is basically GL2, all the 2 cross 2 real matrices. Okay. And now let us give a representation from this C star to GL to R. And the representation, so it will take some number from this, okay, and send it to some 2 cross 2 matrix, 2 cross 2 invertible matrix. Okay. So this is, let us say, cos theta, theta is what is this called? Modulus amplitude. Is this a representation?
There's a rotation. Plus theta 1 plus theta 2 and theta 1.
I'm not sure. Now, first of all, yes, this is of course invertible matrix, cos square theta plus sin square theta. So this is an element of GL to R. Now we have to check whether this Z1, Z2 is essentially Z4, Z1, rho Z2. That we have to check. Okay. So this of course is an element of GL. In this particular case, this is GL2R. And now we have provided a map. Of course, this is a valid map. Okay. So for any Z except from 0, we can always have an amplitude. This is amplitude right here. Now let us see.
This group is under multiplication. What is the operation when we define it?
System under multiplication. So operation is multiplication. Complex multiplication. Number complex multiplication. Okay. So let us check what is rho Z1, Z2. it will be cos of theta, let's call it 1 2 sin theta 1 2 minus sin theta 1 2 cos theta 1 2, right? Where theta 1 2 is
theta 1 plus
amplitude of Z1 Z2. This is nothing but amplitude of Z1 plus amplitude of Z2, which is nothing but, let us say, theta 1 plus theta 2. So theta 1 2 is nothing but theta 1 plus theta 2, where theta 1 is the amplitude of Z1, theta 2 is the amplitude of Z2. Okay, so that's one thing. And what is the right hand side? Right hand side, of course, is cos theta 1, sorry, this will be cos theta 1 sin theta 1 minus sin theta 1 cos theta 1, and this will be cos theta 2 sin theta 2 minus sin theta 2 cos theta 2. So when those two will be multiplied, we will essentially get cos theta 1 plus theta 2 sin theta 1 plus theta 2 minus sin theta 1. Right? So this is another example. So this is another representation. So this is, of course, two-dimensional representation of the complex number, two-dimensional real representation of the complex. Of course, another representation here you can give, that is, you can actually give the what is this? So this is in terms of amplitude. The modulus part we have removed. We can give modulus here. Mod of Z1 times cos theta sin theta minus sin theta cos theta. This is another example. So now this part is clear, because this is the very basic definition, basic thing that from which we will be building on the other things. Okay. So with the examples and all these things, the definition of representation is clear. So representation, basically, if we have a group, whether we can give a homomorphism from that group to the group of all linear transformation, algebraic linear transformation, invertible linear transformation of the vector space. So in order to define representation, that we see is, of course, we need to have a group and we need to have a vector space. So whenever we talk about representation, so we are actually talking about a group and a vector space. So from the group to the linear transformation, invertible linear transformation group, and if we can define some homomorphism, then we can say we have given a representation. Of course, one representation you can always give is trivial representation. A representation will be called faithful representation if rho as a map is 1 to 1. Let's write it down. Our representation is called faithful. Faithful if rho is 1 to 1. If rho is 1 to 1, then it is called a faithful representation. What does that mean? Okay, so can you tell whether this is a faithful representation or not? The last example. Why not?
And many to quantile.
many to one mapping, because the modulus part we are actually ignoring. So any modulus with same amplitude will go to the same vector. So this is not a faithful representation. Example 3 was what? Example 3 was Z2, a representation of Z2, right?
No, that unitary. It
No.
was unitary.
Unitary. Whether that was faithful or not. That was faithful representation. And let us say Z2, representation of Z2 that we have defined. That was a faithful representation in the first example. And what are the other examples? First example, oh, it was Z to Z, so that was also a faithful representation. And what's the time now? It's already 4:30. Okay, then let us stop here. I think the definition of representation is slightly little bit complicated, but since we started from group and vector space and linear transformation, we will define clearly. So now I hope this is not a very difficult thing to remember. So that's why I started with all these things. And okay, so let us stop here today, and then we'll go for other things.